BC 3, 2011. So for part A with this region that we're given, we have the intersection point here is k, and then e to the 2k is ultimately the curve here is e to the 2x. Right? And this is just some some value of k, some vertical line out here to the right of the origin, k greater than 0 it says. And in part A it says write but do not evaluate an expression involving an integral that gives the perimeter of R in terms of k, so R being this region here. And so with that we know that if we want to find the perimeter of this, 3 of these 4 are just line segments. So ultimately that distance from 0 to k on the bottom is just k. So it would be k, and then the height here of this one would be e to the 2k. And then over here on the left, if we put a 0 in, we'd get 1. So ultimately that would be 3 of the 4 parts of that region. And then the other part is what is going to be the length of that? Well, that's why this is a BC problem, because it's curve length that they're asking us for. Okay? And it's not a parametric curve length, so ultimately, in general, our length is going to be the integral from something to something of the square root of 1 plus the derivative squared. Okay. All right. So, with that said, in our particular case, we're going from 0 to k, of course, here. So 0 to k is going to be our two limits, and then 1 plus the derivative of e to the 2x would be 2e to the 2x all squared dx. And again, the issue here though is make sure that we know, we might look at that and say, well, how in the world are we going to anti-differentiate this? And it's not a non-calculator problem. We got no upper limit here that we know, so it's not an integral command type of problem. But bottom line is they said write but do not evaluate. True? So we don't have to evaluate it because they told us to leave it not evaluated. So if we added our 0 to k of 1 plus, and we could, they have it actually in the answer key is this not squared. You can just leave it just like that, or if you wanted to, you could write it as 4e to the 4x. So we have 2x power to the 2, multiply our powers. So either of those versions are good, but ultimately our final answer then would be that. And 3 points for that. 1 if you found the derivative. So if you got your derivative of 2e to the 2x. Okay. And one thing to note here too is that it says specifically to put it in terms of k. Okay. So you don't want to have the dy dx expression here. You actually need to find that dy dx expression, and that's part of the deal. So make sure you do that. 1 point for having the integral, and then 1 point for having the other parts. So basically this part's worth 1, and the other 3 parts are worth 1 also. So if you had, yeah, I'm pretty sure that even if you blew this part right here, if you had that part and plus something that wasn't right, you'd still get the answer point for that. Questions so far? All right, part B then. We got region is rotated around the x-axis to form a solid. Find the volume of the solid in terms of k. So for us, if we were going to do revolving around the x-axis here, we already have our expression written in k, so a vertical slice would be appropriate here. And so if we do a vertical slice around the x-axis, that's going to create a washer. So if we set up our washer method, 0 to k of our pi, and then r squared here, r squared would be e to the 2k squared, or e to the 2x, that is, e to the 2x dx. Okay. All right, and then from there, the question is, can we find this volume in terms of k? Well, if we rewrite our integrand here, we're going to give e to the 4x as our integrand from 0 to k dx. And we can certainly anti-differentiate e to the 4x, where it's itself divided by the derivative of the argument, so ultimately it would be that. And if we put in a 0 and a k, we'd get e to the 4k over 4 for the first part, and then minus, if I put a 0 in there, e to the 0 would be 1, so it would be 1/4. And of course all that is times pi still have a pi out in front. So it should have been pi e to the 4k over 4 minus pi over 4.
Anybody absent?
Ferguson and Kamishik.
Okay, I already talked to them. Anybody absent this morning?
Nope. All good. All right. So, and again, really in the scheme of things for you guys, I mean, it's a pretty simple washer problem. It's worth 4 points. Nice. So 4 points here. We're one, having the integrand right, which means you'd add your e to the 2x squared. So 1 point for having that. 1 point for having the limits. So having your 0 to k. 1 point for the antiderivative. So if you found the antiderivative correctly, a point for that. And then final point was being able to use the fundamental theorem to evaluate. Okay. So 4 points total on that one. Questions on part B? All right, let's see about part C. We got the volume in part B. Changes as k changes, and it says if dk dt is 1/3, then determine dv dt when k equals a half. Well, when we deal with related derivatives like that in instances, that should automatically think related rates here. So keep in mind that we know that v is equal to pi e to the 4k over 4 minus pi over 4. Remember that's what we found. We found v here. We found the volume of this solid. Okay, this volume is going to change as k changes. Okay? If I have a k of 1, it's going to be something. If I have a k of 5, it's going to be something else. The volume is changing with k, it says. And ultimately, how are we going to introduce these dv dt's and dk dt's? We'll just differentiate with respect to time. So dv dt on the left here. And if I differentiate this one, it's going to be pi e to the 4k. When we differentiate e to the 4k, it's going to be 4 e to the 4k, which the 4 and the 4 would cancel out. Differentiate negative pi over 4, we get 0. And remember, I also have to have dk dt here. We're differentiating with the k variable with respect to time. So dk dt, that part. And we know that we're looking for dv dt right here. And we know pi e to the 4 times k is a half, right? And dk dt is a third, it says. So if we put those numbers in there correctly, we got our expression for dv dt. So ultimately it'd be pi over 3 e squared. And that would do it. 2 points, one for applying the chain rule. So if you recognized that you had an equation and you did your derivative with respect to time correctly, you got your chain rule with both of our derivatives introduced. So 1 point for that line essentially. And then final point was have the right answer, pi over 3 e squared. Questions on part C? Okay, move on to number 4 then. So number 4, this problem should look familiar to you because this is also an AB problem. Matter of fact, 3 of the 6 problems are AB problems. Okay. So there's 3 that were exactly the same as the AB test, 3 that were specifically BC. And so with some of our BC information here, let's see if we can come up with answers here. We have a continuous function f. It's in the interval -4 to 3. And the graph consists of 2 quarter circles and 1 line segment. And we know that our g of x function is 2x plus 0 to x of f of t dt. Okay. And so keeping in mind that with the graph of f that we have here, if g is defined as at least partially the antiderivative of f, that means that we're looking at some version of the derivative here. Keep in mind it's not straight up the derivative. In some other problems that we've had, we might have not had the 2x there, and we would have seen that f, if we anti-differentiate f, we get g. So therefore f would be the derivative of g. So it's not directly the derivative of g in this case because of the 2x here. However, if we look at our information that we have here in part A, we have to find g of 3, or -3 that is. And so ultimately if we put -3 into our function, let's see what we can do. 0 to -3 of f of t dt. So of course the first part is negative 6. And then we need the area from 0 to 3 of this function. Well, we can see that going from 0 to 3 is a quarter circle. So if it's a quarter circle, it's going to be quarter pi r squared. And so our radius here is 3. So that would be quarter times 9 pi. So it would be 9/4 pi. Alright, now one other thing that we have to consider though is with this 9/4 pi, okay, are we going to add the 9/4 pi or is it a subtraction situation? And we're integrating something positive, but we're integrating left, so therefore the answer is not plus, it's actually plus negative. So with that said, we get negative 6 minus 9 pi over 4. And if you got that correct, that was worth 1 point. And again, on a non-calculator test, is there any good reason that we should put those together into one fraction? I wouldn't waste the time or take the chance on messing it up either, right? So if you have the right answer, don't mess with it. All right, second part of part A is find g prime. Well, g prime of x, if we differentiate our g here, we're going to get 2 plus f of x. So that is g prime. And like I said, g prime, the derivative of g is related to f. It's not exactly f, it's 2 plus it, if you will. And then they ask us to find g prime at negative 3. So if I do negative 3 into our both sides, if you will, I need 2 plus f of negative 3. Well, we can see f of negative 3 right in the picture. F of negative 3 is 0, so therefore we'll get 2. So 2 points for that part. You got 1 here for finding the derivative of g, and 1 point for finding the derivative of g at negative 3. Questions on part A? Alright, well, let's see about part B then. It says here, determine the x-coordinate of the point at which g has an absolute maximum on the interval negative 4 to 3. Alright, and ultimately, as soon as we see that closed interval, okay, I would use the candidate test, okay, which means that we have one candidate would be negative 4 and one candidate would be 3. Because again, we're going closed interval, negative 4 to 3, and we're looking for the absolute maximum or minimum. In this case, it's maximum we're after. But bottom line is they could occur at endpoints. If there are endpoints in this region, they could occur there. So let's see what our values here are for g of negative 4. That'd be 2 times negative 4 plus the area from 0 to negative 4 of f of t dt. Okay. And so therefore we'd have negative 8. And then our area here, notice that other semicircle, or it's a quarter circle actually, the other quarter circle would be simply pi, pi times 1 squared. So that circle would be pi, and we got a quarter of it, so it's a quarter pi. And remember that one is going to be added to what we had up here. Remember that we have negative 9 pi over 4, if you will, plus pi over 4. And why does the pi over 4 get counted as positive? It's beneath the x-axis, but we're going left. So it's going to be our double negative situations, if you will. And so ultimately, we get negative 8 plus 2 pi as our value. Because I got negative 9 pi over 4 plus 1 pi over 4 would be negative 8 pi over 4. 8 and 4 make 2. So we get negative 8. Whoops, I got it. Not a plus, but a minus. Or negative 8 minus 2 pi, I should say. Okay. Alright, so at this point, you got negative 8 minus 2 pi. We're in the negative 14 some change. So probably not likely to be the maximum here, but still find it anyways. Alright, how about 3? We'd have 2 times 3. Go 0 to 3 of f of t dt. That would give us 6 plus. And this time we have our points that we are going through here are 0, 3, and 3, negative 3. And we can see that if we go down 6 and over 3, that our slope here is negative 2 for that line segment, because ultimately we need to figure out what those areas of the triangles are. And based on the fact that it goes from 0, 3 to 3, negative 3, okay, what could be said about the area that as we go from 0 to 3? That positive area on top and that negative area on the bottom would be the same, wouldn't it? Okay. So therefore, ultimately, how much area would we accumulate? We go 6 plus 0. That's from 0 to 3, we'd have 0 area. That positive triangle would be a 3 by 1.5, but the negative triangle would also be 3 by 1.5. Okay? So we'd ultimately get 6, which is a reasonable candidate for a maximum at this point. So far it wins out of the two endpoints, right? Alright, now, the question is, where else could we get a maximum value? Well, we know that that's when the derivative either equals 0 or where it doesn't exist. Well, keep in mind that the derivative here is 2 plus f of x. And so we ultimately want to know, when does f of x equal negative 2? So that would be our solution to that part. When does f of x equal 2? Negative 2, that is. Well, if you look at the picture there, does f of x equal negative 2 anywhere? Looks like as we move towards the point 3, negative 3, we're going to have to go through negative 2, aren't we? So the question is, how do we find where that is? Well, ultimately that equation for that line right there would be negative 2x plus 3, wouldn't it? So couldn't we figure out what x would give us that? And if we do negative 5, negative 2x, get x equals 5 halves. So 5 halves would be where we have our derivative equal to 0. Keeping in mind that the derivative is f of x plus 2. So f of 5 halves would be a candidate. So let's check out. And again, the question was, though, determine the x-coordinate where it has an absolute maximum and justify. We want to make sure that we do 5 halves in here for our g function because we want to show that it's bigger than that 6. Because that's really our only other candidate. And if we're going to use this candidate test by showing all the possibilities, then we'll rule out the other two if that one is bigger. So let's find out if it is. So we got 2 times 5 halves plus the area from 0 to 5 halves of f of t dt. So we get 5 here. And then our area for our function, we already said that we have on the top, we have a 3 by 1.5 triangle. So that triangle would be 1/2 times 3 times 3 halves. So ultimately we get 9/4 for the top triangle, if you will. And then the other triangle, we're going from 1.5 to 2.5 in that x direction, if you will. And if you can draw this on your paper if you want to, but ultimately we get 1/2 times 1. And the y value at 2.5, if we put a 2.5 into our function here, we know we get negative 2. We already determined that. And so ultimately we get negative 1 as our area for the negative triangle, if you will. And so my overall area then would be 9/4 minus 4/4 would be 5/4. And so what would our total area be here for g of 5 halves? It'd be 6 1/4. Okay. Now does 6 1/4 compare to 6? Definitely bigger. So ultimately that means that at x equals 5 halves, okay, I have an absolute maximum. Because again, by the candidate test, if I list all the candidates, okay, whichever one has the biggest value is the absolute maximum on that interval. So ultimately our x equals 5 halves would be our answer. Alright, so point breakdown is considering the derivative equaling 0. So if you did this part right here, that was worth a point, setting the derivative equal to 0. Okay. And again, it just considers the derivative equal to 0. So if at least you did that much, if you had something about the derivative being 0 here, you get a point. Identify as the interior candidate if you found the 5 halves, if you actually set that equal to negative 2 and figured out the 5 halves was where f of x was equal to negative 2, that's a point. And then the third point was having the correct answer, 5 halves, including the justification. And remember, the justification here is the candidate test. Okay? You've shown that there's only 3 candidates here, and yours is the biggest because you showed this one is 6 1/4 compared to these two, which are clearly smaller. Alright. You also keep in mind too that that's the candidate test isn't the only way to show that that's a maximum either. I mean, you could use the first derivative test here and show that if you did your number line with 5 halves, if I put a number that's less than 5 halves and greater than 5 halves, should have gotten negative then positive. Alright, backwards. Positive then negative. to make that a maximum also. So if you had something like that on there, that's fine too. But I would suggest that anytime that you have the situation where you have a closed interval and we're looking for an absolute max or min, okay, just use the candidate test. How come we didn't need the derivative not exist? And ultimately I got 2 here, and this is f. Is there anywhere the derivative, or is there anywhere f doesn't exist? We have the picture of f in front of us. It exists on the whole domain, doesn't it? Okay. Its derivative doesn't exist, but that's not the issue, is it? The issue is, does f exist? And it does. So there are no candidates where the derivative doesn't exist, so therefore the endpoints and the stationary points are the only ones that we're concerned about. Alright, last 3 points were from parts C and D. So let's take a look at those. So in part C, it says that we want to find all the values of x in the interval -4 to 3, and notice it's not including this time, for which the graph of g has an inflection point. So remember g prime. G prime is this, as we've stated. And if we want to know something about inflection points, then we're going to need g double prime. And we know g double prime is going to be f prime at x. Okay. And we know that we have points of inflection when the second derivative equals 0, or when the second derivative doesn't exist. So therefore our candidates here are going to be 0. And is there anywhere else that the derivative, again, if we set that equal to 0, in our picture, is there anywhere in that picture where the derivative equals 0? Well, at 4 and at 1 from the left, true? 1 from, or at 0 from the left, I should say. 1 or 0 from the right, it's not 0, so therefore it's a corner. So ultimately, that's our only candidate, it's just 0, isn't it? There are no other, I mean, you're looking at the picture right there, there's nowhere else that the derivative equals 0 of that picture. Okay, except at -4, but what do we know about -4? Not part of the interval, is it? Okay. So our only candidate is that that point here in the middle where the derivative doesn't exist. Okay. So if 0 is a candidate, the question though is, does it have a point of inflection? Well, remember, in order to be a point of inflection, it not only has to be a candidate, but it also has to change the slope of our curve that we're looking at. It has to change from positive to negative, or vice versa. And you'll notice that it changes from positive slope to negative slope. So therefore we can say that yes, x equals 0 is a point of inflection. So at x equals 0, I should say, we have a point of inflection. Okay. And again, the justification on that is that the derivative of f, which is the second derivative of g, does not exist, and g prime x changes from positive to negative. So 1 point for that answer and reason. If you got 0 for your candidate and justified it, and then you get 1 point only for that part. And then finally, part D. We have, it says find the average rate of change of f on the interval -4 to 3. Okay. So if we want the average rate of change of f on the interval -4 to 3, if we take our f -4 and our f of 3, okay, so our average rate of change, our f of -4 is -1, and our f of 3 is -3. True? And we're looking for the average rate of change of f. Okay, all that is the slope between the endpoints on this f curve. So if we calculate the slope, -3 minus -1, 3 minus -4, you get -2 on top and 7 on the bottom. So we get -2/7. That'd be our average rate of change. That's worth 1 point. So if you calculated that slope, you got a point for that part. All right. And then ultimately, the rest of it's a mean value theorem question. It says there is no point C between -4 and -3 for which the derivative is equal to the average rate of change. Explain why this does not contradict the mean value theorem. Again, with our picture looking something like this, here's our 2 endpoints. Okay. And the question is, why is there no place in between these two where the derivative is the same as the slope between the endpoints? It's not what?
Differential.
It's not differentiable. Exactly. It's continuous here. And this function is continuous on the entire interval, but it's not differentiable on the interior. It's not differentiable at 0. And so therefore the mean value theorem does not hold. And ultimately, last point was for the say on that. Okay, so that's all you had to come up with, the fact that it's not differentiable, so therefore the mean value theorem does not hold.